Lingling Mao is from the Southern University of Science and Technology in Shenzhen, and the title of her talk is A Rational Design Playbook for Functional Hybrid Metal Halides. Please welcome Lingling Mao.
Right. Thanks so much, Andy, for the nice introduction. First, I would like to thank Tony and the organizing committee and also His Highness for this great event, and also inviting me to come here to present some of our recent results on hybrid metal halide. So Professor Osman Baka has made a great introduction and overview of the perovskite solar cells. So my background is actually similar to that, and I'm sorry. Okay. So I think that this slide, I don't need kind of further explaining the sort of the improvement of the perovskite solar cell. And I was a graduate student back then with Makary Halides, and we were at the time working on the two-dimensional materials that kind of can be seen as this 3D perovskite, which Professor Osman Baka has explained, right, with some of the relatively limiting compositions. But if you put a larger organic cations within these inorganic layer of the lead iodide, then you can make these layered perovskite materials from different N numbers. So at the time, I was working on this so-called de Jong-Jacobson phase, which we can systematically tune the layer thickness and also, the sort of the property, specifically the optical properties and also the optoelectronic property. As you can see, the color goes much darker as the layer thickness increases. So it's becoming more like the three-dimensional perovskite, and then this is the ideal color for absorbing solar energy. And at the time, we also work on some really relatively extreme to the high layer number, which is n equals to 7. Even though there's some of these so-called quasi-perovskite, 2D perovskite that claim to have like n equals, 20, 40. But I believe that it's very difficult to characterize. So at the time, we were able to characterize it with a single crystal XRD and then sort of identifying these phases. So think of sort of the design space of perovskite material and also the related metal halide. It's sort of opening it up, really, if you go from the 3D to the low dimensionalities, because you can incorporate all of these different organic species, right? Really like Professor Omayagi's work, right, in MOFs. So you have a lot of these organic linkers. But here, because these layers and the organic cations, they're not linked directly, so that they have these sort of mainly hydrogen bonding interaction between ammonium groups with the layers. But then also you can make all of these cations viable and then change the properties of these materials. Another important point in this sort of design strategy is to choose the metal, because we know that for these semiconductors, right, we start from these main group metals, right, the lead, tin, germanium ones that show high promises in this area. But then if you choose other metals, then you can also bring different properties. So we're pretty much looking at different metals and how to incorporate these metals with the organic part to achieve new structure and new functionalities. So for the generic metal halide, there are actually a lot of interest in different areas. For instance, if you look at the solid-state batteries, these lithium halides are good for the superionic conductors for these batteries materials, and also the chromium iodide is famous for the magnetism that you can tune with different thickness. And in our group, we're mostly focusing on looking at the non-centrosymmetric phases, basically just breaking down the symmetry. Because most crystals, if you look at the database, they crystallize in centrosymmetric space groups. But if you break down the symmetry using different strategies, new phenomena and physical properties will emerge, such as some of these circular polarized luminescence or nonlinear optical properties and ferroelectric, etc. So here we have basically working on 3 systems so far. The germanium perovskite, which is kind of a special family of the perovskite materials, but it has a very active lone pair so that it can induce a non-symmetric space group at room temperature. And then also we can use the alkaline metals to form these coordination that breaks down the symmetry with the organic cation ligands. And more directly, if you use a chiral cation or ligand itself to bind or interact with the inorganic part, then it will directly self-assemble into these non-symmetric materials. So here, just to kind of show a little bit difference, right, between the perovskite materials and also the lower dimensional ones that are light emitting, have very strong light emission. So these ones, right, the perovskite, the emission comes from the band edge, right? So you can see this color, and then the emission energy is close to the band gap. But for the, for instance, right, for the manganese compound in low dimensionality, the emissions, right, are more kind of sensitive to its coordination and also the coordination environment, so that this is not a sort of a semiconducting emission, right? It's coming from the metal itself. So our first sort of, not first work, but to start off with the highly emissive material that we are aspired to explore is this work that's published almost 3 years ago in JAX that report this sort of a metal, dual metal centers with the solvent to coordinate with one of the metal, and then the other part is just a normal sort of halide composition. And then in this work, they reported the crystal to glass transition and also very high emissive photoluminescence from the antimony unit. So got immediately intrigued by this family of materials, because you sort of, with the new sort of the A component, right? For perovskite, it's just a small cation, but in the system, right, it's a sort of a complex itself, so that you have more variety to look at the different structures, families, and new potentials. So if we wanted to find similar materials in the history, in the literature, it's actually can be dated back to maybe the 70s or even earlier, so that I think it's a cobalt complex with different ligands, and then the anionic part is zinc chloride materials. Okay, so when we look at that, we got immediately inspired. So we don't think that it should only be limiting in this report that reported a few new compounds. So we look at based on the sort of this general formula ALNBCLM, right? So there are many different parameters that you can play with, right? You can change the A metal, which here we chose ranging from the alkaline metals to the lanthanides and also some of the transition metals. And then you can change the solvent ligand, and in this work we ranging from DMSO to TMSO. And for the B metal centers, here we're looking at the antimony, bismuth, and tellurium. Okay, so you can see that all of these many new compounds, they have different structural types, right? But they look quite similar, but it's in fact quite different if you look at the properties. So to first look at the emission properties, the antimony materials, right, generally have a very high photoluminescence emission efficiency, and then sometimes you also see the emission of the rare earth ions. But then for the bismuth one, it's generally much less emissive, which is signature of the bismuth halides. So you can see the emission from the terbium, europium here just much more obviously. And then if we look at the geometry that relates to these emission properties. For instance, right, this is a magnesium DMSO6, antimony chloride 5. So these green ones are the antimony ones, and the center is the sort of coordinated center. So emissions are coming from here, but then this unit, right, it will subsequently affect the emission and also the sort of the formation of these units. So you can see that when you change the excitation from different wavelengths, you can see a coexistence of the singlet and the triplet emission, or you can only see the triplet emission at lower energy. But then if you look at a different sort of structural type, which is here antimony chloride 5, with the same formula, but this is a different coordination geometry, I think, a square pyramidal one. So you see the sort of the difference when you change the excitation from here only the singlet and here only the triplet. So we make sort of a summary for this phenomena that we observed. So for the perfect octahedral antimony chloride 6, you only see the triplet emission no matter what kind of wavelength you're using. And then for the sort of a different pseudo octahedral or the square pyramidal, which you can see the long pair, which should be underneath here, that has a more static effect that you can sort of see the coexistence of both of these emissions. So in following it up, right, we wanted to really see how these systems can change a little bit more, right, from a different direction. So as I mentioned earlier, the antimony chloride 6 is quite persistent, right? You can almost only see the emission for the triplet. But then if we further change the sort of a coordination here from 6 to 8, right, 8 to 6, so you use a larger solvent, a ligand in this case, then you see sort of a emerging shoulder in this case, and the main sort of highest peak, right, has blue shifted. So for this system, we think that it's because of the sort of the symmetry of the local octahedral that is much more influenced by the coordination of the rare earth elements here, so that this whole thing is still a triplet emission, but with a much higher distortion at the excited state. So we follow it up, right, with sort of another side of tunability, which is still on the solvent ligand. That is, you can put, let's say, a chiral, right, a chiral composition within it, so that the whole thing self-assembled. But this is a zinc system, so slightly different from the antimony one that has a blue emission and then apparent different wavelengths determine SHG signals. So following up that work, sorry, I think this slide is slightly messed up, should be in the next slide. But this is actually correlated to the two slides earlier, that the melting temperature of these materials can be changed if you're using different sort of the rare earths with the increasing ionic radius. And then the melting temperature will directly increase, right, ranging from 140 degree to 200 degree. But I think in the original Jack's paper, they reported the melting temperature to be much lower, but we're basically using different compositions, so that's sort of obvious, right? So then you can see how it from 200 to even lower to 90, right, if you link all of these together. So this means that we can change the temperature, and then you see an obvious effect in the in situ powder X-ray diffraction, right? When you increase the temperature to 140, then it becomes close to amorphous, right? So that this time it shows the emission from the lanthanide ions. And then here, if you go back to the room temperature, it's showing the triplet emission from antimony. And then if we are trying to, again, think about it, right, to tune the emission property from another handle, which is pressure in this case. So we can see really from the 3D to 0D, right, the perovskite structural prototype, the compressibility of this crystal, right? So perovskite, I think halide perovskite should be considered generally relatively soft, so you can, it's relatively sensitive to the pressure stimuli. So the bulk modulus here quantifies its compressibility. So you go from around 40 to 20 in the literature report. But then if we look at this system, right, so we change the chloride to bromide because of a wavelength excitation sort of restriction in this case, then we can see really the bulk modulus go really high up at some point when you increase the pressure. So this has to relate to the hydrogen bonding strength with when you change the different solvent ligands, right, from the DMSO to DMO, and then this hydrogen bonding become much more stronger, so that when we increase the pressure, especially they have shown really a much similar trend, but also slightly different, because you can see how the intensity of the emission has peaked at around 2 gigaparts, right? Yes, and then it just starting to decline, right? So the first two compounds doesn't show a sort of a dramatic decrease, but for the last one, right, it shows a much sort of instant quenching of it. And then you can see how the bulk modulus suddenly becomes sort of higher up, right? Because really, I think a phase transition here, so that it becomes really rigid and then very difficult to excite under this situation. So another related work that we're trying to use high pressure to break down the symmetry in the two low-dimensional tin bromide system. So if we look at here, using this sort of a cation, that doesn't look too different, right? But the special thing is that it has a CF3 group, which the fluorine can be very highly electron negative, right? So in this two-dimensional perovskite materials, if you are starting to apply pressure, so it shows that so the original structure is centrosymmetric, but then if you increase the pressure, right, starting to show second harmonic generation, meaning it's starting to become a non-centrosymmetric. So it peaks at around 8 gigaparts and then starting to decline. But then this, when you release completely the pressure, it has this effect of still, right, the SHG signal. So it means that it got retained the non-centrosymmetric structure even under this kind of, so it should be usually reversible, right? But then at this point, we can also see that the absorption of these two phases has changed significantly. So you maintain sort of a lower energy emission. And then if we look at the in situ synchrotron XRD, the different phases, right, can be seen in this plot. So we are very curious by this effect because this has generally never been reported and cannot really retain this non-symmetry. So if we further really change the composition, and we can make a one-dimensional compound, and it has a similar effect. So I didn't show here the structure, but you can see how this CF3, right, has really flipped this ring, right, and then this structure we collected back at ambient conditions and intensifying FF interaction in this material sort of as a glue to hold this non-centrosymmetric structure. So this actually reminds me of our one of our previous work, which we're using the copper iodide system to make these very highly emissive materials as well. So we actually use the same cation. And so here, the difference is that it has a coordination between the nitrogen, the pyridine ring, right, with the copper iodide clusters. So these are zero-dimensional ones. And it's really sort of uncommon, right? So generally with a few polymorph, maybe 2 under room temperature is normal. But then here, at least we have collected 4 different polymorphs using the diffusion method to make these materials. So you can sort of handpick all of these and then make the emission spectrum to see how really it different from each other. So this really reminds me that how this interaction can be very unstable and dynamic. So I was really intrigued by it. So maybe we can do something more about it, right? As this very interesting sort of interaction that can bring a lot of new functionalities. So for the copper iodide one, we also have done sort of a similar jobs related to that, similar work that has this monodentate ligand or the bidentate ligand, that's chiral, because I mentioned that we want it to be non-central symmetric, and by using these ligands, right, the chirality will be transferred to the overall framework of these materials that shows circularly polarized emission. And then if we don't, again, switch back to not coordination, but just a hydrogen bonding interaction in the layers, you see this kind of a honeycomb kind of a framework with the copper iodide. But the emission is much lower in quantum yields, so it's kind of reasonable because the copper iodide species generally with the copper clusters, they have the highest sort of emission properties. But then if we sort of use this as a starting point, we can make some of these lead octahedral to replace some of these copper dimers so that you can form a new structural type which has a copper dimer with the sort of interconnected lead materials. And then we also sort of characterize its circular polarized luminescence and also the emission and SHG properties under high pressure. So our last part of my talk is really something that when I was a postdoc with Tony and Ram at UC Santa Barbara, we are back then working on these manganese compounds that has a very high photoluminescence quantum efficiency. So these materials actually have been reported, again, very early on, and there are a lot of compounds of structures and emissions, the properties that have been reported. But then I think, and also it's easy to get these isolated tetrahedral just by changing the organic part, right? So you can choose either like a really small cation to a very large one that sort of very flexibly can change the distance between the manganese center. So at the time we found that it has, the emission property has something to do with the manganese distance, where you can change it really to a very high long distance that's similar to a effect of the concentration quenching, right? So if you have the emission center to be closer to each other, the energy recombination can easily happen. So if you put them further apart, right, so that would be helpful for these emissions. So when I was back in Sussex, then I started to work on, again, right, using these highly emissive materials to do, again, either a coordination or non-coordination compounds, so that we found that it actually helps to increase the chirality with the coordination to enhance the dissymmetry factor of these emissions. But then some of our recent finding involves a really complicated system that historically have been called a clusterate. So these clusterates, right, well, I guess it's not a very popular name at this age, but then it again involves a lot of different compositions, so maybe even more complicated than the solvent coordinated system. So you have this counter anion, which doesn't do anything pretty much. But then you have the emission center, which is the manganese. And then you have these crown ethers coordinated with the different alkaline metals. Historically, we know that for the C18, right, crown ether, potassium has the best fits of all of them. And then we found that this actually affects the emission of these manganese center. So we demonstrated using two different ways. One thing is that we change, so we make a solid solution out of them, and we also change the halide, in this case, from chloride to bromide. Okay, so just to make it slightly shorter, because this slide might be really complicated, when we do the solid solution, the alkaline metal has a preferential sort of which side they are going in, and then this further sort of influence the structure and also the emission quantum efficiency of the manganese compound. And then you can see how the original thallium ones that has this closed shell clathrate structure, and then in our case, the indium one has some relatively open shell geometry in this case. And then just to conclude, right, the ideal case is using the potassium one, which has the best fit with the crown ether. And also you can see how it changes the emission, which generally doesn't do that in the magnet system, that if you have the bond length to be slightly shorter, then that will further affect the ligand field strengths of it and then change the emission. Okay. All right, so just to wrap up, so we published a few of these review work on perovskites and other applications such as non-linear optical properties and ferroelectric, and also our upcoming perspective of our mostly the development of this hybrid metal halide that's other than the perovskite materials, how they will, we can tune them and change their properties. Okay, finally, I would like to thank all my collaborators, which of course supported me in our research throughout the years, and my group members who have done really amazing work on the exploratory part. And also welcome to visit SUSTEC in Shenzhen. This is one of our, I think, teaching buildings, and this is the business school that are sort of linked through this bridge. And then Tony visited last, I think, by the end of November, so it's a good weather at the time. And also, I would like to thank my advisors and also this funding from NSFC in China, and also our school startup funding. Okay, thank you for your attention.